Okay, so why don't we get started? Today's topic is basically just a review of functions. So I hope I don't bore you to death, but hopefully this is something you know already. So the first place I like to start when I talk about functions is an analogy. I like to equate a function to a vending machine. Has anyone ever heard me give this example before? So I think I did it with my 20-1 kids last year. So I like thinking of a function like a vending machine. When I go to a vending machine, I put in a loonie, and the vending machine gives me back a bag of chips. Does that make sense? You give something to the vending machine, it gives something back. Okay. That works really well when it comes to functions because functions are basically relationships between variables. The variables in the vending machine would be $1 and a bag of chips. Those are your variables. Only in math, we don't use those things. We use x's and y's. Does that make sense? So we're trying to write equations that have x's and y's, and sometimes rather than writing y, we use this fancy notation right here, f bracket x. And the way that we say this particular thing here is it's called f of x. If you're ever wondering how to say that notation, it's called f of x. I think I have a slide later in my notes that kind of describes the f bracket x notation. But have you guys ever seen that f bracket x notation before? Okay, I can explain a little bit better later. But long story short, our goal is to deal with inputs and outputs. So let me go back to my vending machine example. What is the input in my vending machine? Money. Which in math examples is the x value. Whatever the x value is your input. And then based on what you input, you get something back as an output. So in the vending machine example, your output would be like your chips or your chocolate bar. And there's lots of different inputs and outputs. For example, I could put in $1. I could put in $2. I could put in $5. That makes sense? I could get back a chocolate bar. I could get back a bag of chips. I could get back a stick of gum. That makes sense? So there's multiple different outputs and inputs. For the most part, the functions you guys should have learned so far, you probably would have learned that all inputs and outputs are probably valid. But that's not always true. And we're going to talk about some exceptions this year. The analogy I like to give here is, let's say you try to put in 10 cents. Can you get anything out of a vending machine for 10 cents probably? I would say probably not. Right? So that might be a domain that's not possible, where it's just not physically possible to put in 10 cents. The graph just does not exist in that location. And the same thing happens for the range. The range is the outputs. For example, if I go to a vending machine, is it going to sell me cigarettes? Well, I mean, if you're in Japan, actually, I think they do sell them there. But
They do have beer and stuff.
Okay, but could I buy a motorcycle out of a vending machine? Could I buy a leprechaun out of a vending machine? Right. Well, I guess I'm going outrageous here because is every single possible thing that I'd want to buy available in a vending machine? No, so there are going to be some restrictions. So one of the main things I need to focus with you guys on this year is what is the domain and range? What x values are valid? What sort of things can you input? And conversely, what things can't you input? And then same thing for range. What sort of things can you receive back and which ones can't you? When it comes down to it, functions are equations. Okay. We've done a little bit of work with equations already this year with all of our algebra unit. But at the end of the day, you plug in values of what you know, which is domain, which is like an x value, and you use it to find an unknown value, a y value. So I've got a couple examples of just some very basic functions that you probably would have learned way back in junior high. Could you write me an equation for the area of a circle as a function of its radius? Fancy way of saying this is, does anybody know the formula for area of a circle? Close. Area is pi r squared. R squared. It's close. You actually have circumference. You have circumference. So as an equation, when you guys are in other subjects, like say physics or chemistry, I mean, equations are essentially functions. I could write this as y equals pi x squared. Does that make sense? Like the a and the r, does it really matter what letters I use? Probably not. What often we do then in math is we don't write it quite like this. We would write it in this format. We'd write a bracket r equals pi r squared. And this is that similar to f bracket x notation. Now, let me see if I can explain why we do this, because it seems random, but there actually is a really good reason why. The thing in brackets is the variable you have to have later. Okay. And maybe I can use the example you tried here for a second to try to illustrate the difference. Anybody ever seen the formula circumference is equal to pi times diameter? Or sorry, no, not two diameters. Pi times diameter. Anyone ever seen that formula before? Well, that's the formula for all the way around the circle, circumference of the circle. Okay. Well, the way I would write that then is that the circumference with the diameter as my variable is equal to pi times d. But that's not actually the only formula for that. Maybe you've seen this formula. Circumference is equal to 2 pi r. Anyone ever seen that formula? They're both formulas for circumference of a circle. The difference here is that I would have to write it as the circumference based on a radius is equal to 2 pi r. Long story short, the whole reason why we go with this f bracket x notation is just to let you know that x is our variable. If I wrote f bracket z, your equation would be pi times z. If I wrote f bracket smiley face, your equation would be pi times smiley face. Does that make sense? So, long story short, this is a fancy way of saying y. Let me skip the other examples. I don't think we really need them. Here are some of the main ways that you've hopefully learned in the past of how to represent a function. Sorry, I'm going to close that window. That window's really distracting me. Okay. The four main ways are to write a table of values. If you input 1, you get back 2. If you input 2, you get back 3. If you input 4, you get back 5. Another way you could write it is as an ordered pair. Well, ordered pairs and table of values, they really look kind of the same way. Like 1 gives you 2. A 2 gives you 3, a 4 gives you 5. A third way you could do this is you can make a graph where you could say this is where the 1 is, that's where the 2 is, so this is 1 with 2. This is 2 with 3, this is 4 with 5. Does that make sense? But probably the biggest challenge I have for you guys is we need to be able to write an equation based on this. So go back to the vending machine analogy. If you input $1, the vending machine gives you back 2. And if you input $2, it gives you back 3. And if it inputs you back $4, it gives you back 5. How is this vending machine set? What's it doing every single time? What's the pattern? Pardon me. The y value is 1 more than x. Yeah, that's essentially what's happening, right? If I put in 2, I get back 3. If I put in 3, I get back 4. So if I gave it $1 million, it would give me back $1 million and what? Does that make sense? So the way we'd write this as an equation is the output is equal to the input plus 1 more. Or maybe the other way we'd write it would be like this. F of x equals x plus 1. Both of these would be valid. I need you guys to be a little more comfortable with the second method, with the f bracket x method, because that's probably what you're going to see. Let me give you some examples of some other functions. Let me give you a rule here. The rule would be the vending machine triples your money and then subtracts $1. Your vending machine triples your money and subtracts $1. That would be your example. That would be 3x minus 1. Yeah. Or let's say the vending machine always gives you back $1. Y equals 1. Yeah, if the vending machine always gave you back $1, you put in $1 million, it gives you back 1. You put in 5, it gives you back 1. You put in 0, it gives you back 1. Essentially, you're always getting 1, so that your equation would be y equals 1. Maybe you've heard these words before, the terms discrete and continuous. Discrete basically means that you can't have partials of things. If you were in my 20-1 class last year, one question that came to mind was a hot dog vendor selling hot dogs. Realistically, you can't sell like 3/4 of a hot dog. I mean, okay, maybe you could sell 3/4, but could you sell 0.95732 of a hot dog? So like discrete basically means you have to sell things in whole numbers essentially, maybe half numbers, Whereas continuous means you could have any single number possible, including like the most random, obscure decimal number ever. Right? So like this example I pulled somewhere off the internet here, the number of pages in a book is discrete. It's either 1, 2, 3, 4, or 5. You might argue that someone rips out a page, but like, you know what I mean? Like it has to be a whole number essentially, right? Shoe size is still discrete, even though you can have like 5.5. I don't think you can buy a shoe in like 5 7/19. Like they won't sell you a shoe with that, right? But if you look on the other side here, temperature is continuous variable. Could the temperature be 25.937 degrees? If we had an instrument able to measure it, sure, I guess we could. Could the time be 11.9237 seconds? Could it be something ridiculous like that? Sure. Time is not measured just in 1 or 2 or 3 seconds. You can break it up more. So the reason why I point this out, though, is that a domain means that you might only be able to input certain values. So let me go back to the vending machine. Would a vending machine accept $1? Probably. $1.50? Probably. $1.62. Seems unlikely, doesn't it? Right? I doubt it, especially now that we got rid of the penny. Right? And so sometimes there's certain domains that you just aren't allowed to use because it's just not logical. And that's going to be part of what we focus on is what numbers are valid and what numbers are not valid. Okay. So let's try an example here. Here's a parking lot. It charges a flat rate of $10. Then you got to pay $3 an hour for usage. My goal here, we're going to try to represent this information in the 4 different methods. So we're going to try to write a table of values, a bunch of ordered pairs. We're going to try to sketch a graph. And then after we do all of that, we're going to try to write an equation. So I find the table of values a good place to start. X and Y is a good place to write them down. But maybe rather than X and Y, why don't I say that X is like the amount of time that you're parking for, and Y would be the amount of money you have to pay? So that's my first question. Give me an amount of time that would be valid. Sure, 1 hour. How much would it cost you? How much would it cost you if you parked for 1 hour? $13 per cancel. 3 plus 10, right? Because you got to pay the flat rate of 10.
Would it be 10, 0, then 10, 3?
So that's actually a good place to start. Actually, if you parked for no time, I mean, if you just walked into the parking lot and then came back out again, I mean, so long as it could catch you, you should actually pay $10 just as your flat rate before you even go anywhere, right? Let's do one more. If you park for 2 hours, your flat rate of 10 plus 3 means 16. That's probably good enough to start. Let me get to that though. You're gonna have it right though. Another way we can write it then would be like this: 0 with 10, 1 with 13, and 2 with 16. That's the second way. The third way would be a graph, and you guys are going to do a lot of graphs in this unit. So let me show you my expectations of a graph. Mine are very, very simple. When you draw a graph, I need you to draw no ruler. Don't worry about like putting on grids and stuff like that. You can just draw a T like this. Okay. I do require you to label where the graph goes from. So for example, maybe this goes back as far as -5. Maybe this goes as far as like +5. Maybe this goes down as low as -20. Maybe this goes as high as +20. I don't care what numbers you put on the edges of the axes, but please tell me what those numbers are going to be. Does that make sense? And I'll show you how in your calculator to find those window sizes later if you don't remember how. And then basically just roughly plot where they'd happen to be. So 1 and 10 would be about right here, I guess. And then my other expectation is if you're plotting a key point, actually like put the coordinates next to it. So like that's 1 and 10. 2 and 13 would probably go ish right about there.
Isn't it 0 and 10?
Good catch. Thank you. Woo. Thank you. Okay. 0 and 10 should go here. 1 and 13 probably goes about here. 2 and 16 goes here. This is my expectation of a graph, by the way. That's all I would require. Okay. Give me an axis. Tell me the edges of the axis so I have some idea as to where the graph is going from. And if you plot a point, label it. If you wanted to, by the way, you might argue that like this whole section of the graph over here wasn't even used. So another valid way that I would accept a graph is if you drew something like, say, this, and you said it went from 0 to 5, And you didn't even have to start as low as 0. You could start this maybe at, say, 8 to 20. And then if you plotted those points, 10, 0, and 10 would be probably about right here. 0 and 10. 1 and 13 would be about there. 2 and 16 would be right about there. That would also count. Does that make sense? Okay, Latoya, give me an equation.
I put x equals 3x plus 10.
You got it. And there's our equation. 3x plus 10. Depending on how many hours you're there, cost you $3. And then 10. Review from previous years?
Yeah.
Excellent. Okay. I am going to be excited if I bore you today. It's rare that I would say that as a teacher, but if you're bored today, that's a good thing. I'm sorry, but it's good. Okay. So maybe you've heard the phrase linear data before. The grade 10s down the hall in grade 10, they're learning linear stuff for the first time. And like they're going to take, I was talking with Mr. Kwan about this, they're going to take like weeks to talk about how to graph linear data. I'm going to give you about 4 minutes and then we'll move past it. Because like you've probably seen this before, right? Like you know how to plot a straight line, right? So the equation usually fits this pattern. Y equals mx plus b. Yeah, we're like 3x plus 4, y equals 2x minus 2, right? You guys remember doing this stuff? The number that happens right here is how steep the graph is. And this number right here tells you where the y-intercept happens to be. So let me go back to the graph we just did. Latoya gave me the equation y equals 3x plus 10. If I were to put a line through all this data, 3 is the slope. That tells you how steep the graph is. The bigger the number, the further steep the graph happens to be. Does anybody know what happens if you have a negative slope? Yeah, it goes like downhill. So like a negative slope would go like that direction. The b value, which in our case is the 10 tells you where this location is, called the y-intercept. And the y-intercept is basically where on the y line it crosses. Because this is y and this is x, by the way. Still good? Cool, moving on. Okay, this just talks more about function notation, just the idea that you could write it as y equals 4x minus 2. You could write it as f bracket x equals 4x minus 2. Please don't split hairs over the difference between the two of them. They mean the same thing. The only reason why is that this just indicates what variable you're using. Traditionally in math, we go with x and y. But when you get to higher levels of math, like when you go to university, if you take math courses there, you might not just work with x's and y's, you might work with x, y, and z, for example. And x and y works really well in 2 dimensions. If you try to solve problems in 3 dimensions, you have to go x, y, and z. In physics, sometimes you have to go 4 dimensions. Anybody know what the 4th dimension is? X, y, well, no, x, y, z, time actually is the 4th dimension sometimes. So, I mean, you usually work with, usually for like high school kids though, x and y is sufficient. Okay, moving on. Here's another picture of a graph. Let's just talk through the basic properties. There's a number right here, -2, that's the slope. This helps explain why the graph is going downhill. That hopefully is a review. That's your slope. When you typed in -2x plus 1?
Yeah. Going this way.
Interesting. Let me continue. Because you still doing 4x minus 2. I'm on the next slide. Okay, the 1 value afterwards here, this is your y-intercept, which we can visually see on the graph right there. Now, I've got a few different terms I need you guys to know. Slope and y-intercept is probably what you've heard in the past, but here's 2 other words I'd like you to know about. One of them is called a leading coefficient. Anybody ever heard that one before? I might have used that with you guys last year. Do you remember that term?
Vaguely.
Okay, the leading coefficient is the very, very first number you have. Only rather than just talking about linear graphs, when we talk about every other graph, we talk about this unit here. The very first number is the leading coefficient.
So is it like -2?
Yeah, so -2 is your leading coefficient. So in this example, it's still the slope, but it's also the leading coefficient is the more broad term we'd use. And the broad term we'd use for the y-intercept is sometimes called the constant term. And a constant term is a more broad term that we would use across all functions, where the reason why it's called a constant is that there's no x's attached to it. Okay? X is a variable, which means we don't know what x is going to be. X could be 1, 2, 3, 4, 5, 17.2. But I guarantee you this number 1 is always going to be the number 1 because there's no x next to it. That's why it's called a constant term. Okay, let's draw a graph here, and then we're going to use our graphing calculators to remind you of how to do certain things. So I like to think of this as a machine. Here's a rule, negative 2x plus 8. What this means is give me a number, times that number by negative 2, then add 8. So in terms of what I would ask for you to do here, let's start by graphing it. Do you need a graphing calculator?
Yeah. My batteries are.
Yeah, I know. Okay, so if you hopefully have the same rough calculator as I do on here, first thing you got to be able to do is turn it on. Go to your y equals screen. And mine has some random stuff in there from the last time I did that, so I'm just going to clear it out. I need to really teach you a lot of little troubleshooting issues. Up here, see where it says plot 1, plot 2, plot 3? Make sure that none of those are highlighted. Later, I'm going to show you why you might have them highlighted for some reason, but make sure they're not currently. Also, over here on the far left side, do you guys see how there's like a regular little different little line going down there? If you wanted to, you could go over, like press backwards, press enter, and you can make one of your lines be like a thicker line. And sometimes that's useful if you have to have more than one graph and you want to know which one is which. But I think at this point we can just start typing in our graph. So I'd type in little negative 2, then x plus 8. Everybody okay with that so far? Do you have a graphing calculator?
No.
Here, let me lend you mine for right now, just so that you have one of the TI-80 ones to work with. Is this your phone? How about the same sort of phone? Okay, well, try this one for now, and then let me work with you on your phone.
Can I do it right?
You're going to need a graphing one for the...
Right.
Okay, one of the things I always suggest to students then is don't just press graph right away though, because it really depends on what your window size is set at, and who knows what the previous one you were working with was. So right next to y equals is the button window. Currently my graph is set to go from 0 to 360 and from negative 5 to 5. That's kind of a really weird range to pick. So one of the fastest ways to kind of get back to a really normal window size is to press zoom and then to go down to number 6. Thank you so much. Yeah, that is perfect. You're awesome, Bobby.
I know.
If you press zoom and then standard for 6, it takes you to a nice 10 by 10 grid. It's a great place to start. And hopefully your graph looks like mine, only mine is a thick line. You might not have changed it to a thick line, but everyone has one that looks like this. So here would be my expectations when you graph this. When you graph it, you would have to tell me what your window size was. So I'm currently going as low as negative 10, as high as positive 10. I'm going as high as positive 10 that way, and as low as negative 10 that way. And the graph looks roughly like that. And I would be content if it was roughly in that location. I don't need you to actually go through and find exactly where it is, because here's how you're going to fix that problem. We're going to label some points. And I've actually given you some points here to look for. So I want to talk about this notation here. If it says f bracket 2, you know how the equation normally says f of x equals minus 2x plus 8? I mentioned earlier, if I told you it was f of smiley face, all you would do is change your x into a smiley face, which is a kind of down face. But what if I tell you f bracket 2? Well, f bracket 2 means rather than writing an x, write in the number 2. Well, when you do something like that, now there's no longer any variables left. We've actually input a number. I've input the number 2 into this graph. And it's going to tell me what the answer happens to be. And maybe the best way of doing that is to go to, say, your table of values. Does anybody know how to get to your table? Okay, press second, which is the yellow or blue button, and then graph to get to your table. Now, my table currently is starting at the number 100, and then it goes to 100.5 and 101 and 101.5. So I want to show you a bit about how to change your table around in case yours is screwy like mine. So you see above the window right here, it says TBL set. Go second window to go to table set. And here's a few things you can kind of mess around with as well. See how mine says table start equals 100? This explains why my table is starting at the number 100, which is kind of dumb. So I'm going to have it start at 0, I guess. And do you see this little triangle right here? And then TBL? A triangle in science is a short notation for the word change. So this is how much the table changes by, and it's going up by 0.5s. That's usually odd. Usually we don't go up by 0.5s. Usually we go up by 1s. But if you want it to go up by 1s or 2s or 5s, then you can do that too. So I'm going to restart my table at 0 and make it go up by 1s, and now I'm going to go back to my table. And as I look at the table, if I plug in the number 2, what output do I get? Yeah. If I plug in the number -1, I'm just going to go up on the table here. -1 would spit me out a 10. Or if I look at the number 3, 3 should give me a 2. Essentially what your calculator is doing for you is it's taking the equation, and in the location of the x, it's just inputting a number. Okay, so then we got to talk about that one. The y-intercept occurs when x is 0. That's the definition of a y-intercept. The y-intercept occurs at f of 0, which is 8. Which I could have told you anyways, because look at the equation. What is the constant term in the equation? 8. So that's where it is. There is another way to do this, by the way. In your calculator, if you go second, trace, and you go to this screen here called calculate, this will do essentially the same work for you. Press the number 1 for value. It should re-pull up your graph again, and down in the bottom corner, it should say x equals, and it should be flashing in front of you. And then, yeah, just basically tell you what you want to know about. So if x equals 2, it gives you y equals 4. And the cool thing here, by the way, it will actually put a little x on the screen telling you where it happens to be. Let me show you where you might come into a problem, though. Let's say I go second, calculate the value when x is 25. And then I try pressing enter. It gives me an invalid. Anyone want to hazard a guess as to why it couldn't handle 25? Yeah, the domain of your graph, the window of your graph was set to go from 10 to 10. So if I wanted to try to find out 25, oh my goodness, there we go. If I wanted to find out 25, I'd have to change the window of my graph so that it was going at least number 25. If I wanted the y-intercept, second calculate the value when x is 0. And there it is right there. There's your x-intercept up at 8. So far, so good? Thoroughly bored? I hope so. Okay, moving on. Did I have a blank slide after that one?
Linear equation should also always have one solution.
Oh, okay. For some reason, I got a blank slide in my copy here. Whoa. Okay, I want to talk a bit about the concept of a solution. If you ever get asked to solve an equation, the way solving typically works is you're being asked to solve for x. Does that make sense? So solving means we're actually going to tell you the y value, we're going to tell you the output, and we're going to make you work backwards for x. So if you think of it like a machine, rather than me giving you the input and you find the output, which means I give you x, you find y, if you're ever asked to solve, I'm going to give you y and you find x. So let me try an example like that. So here's a graph. Let's sketch a graph of 2x minus 4. So go back to y equals and change her up. 2x minus 4. Before I even type in the graph, I should know a little bit about the shape of the graph. Because the 2 is a positive 2, the graph should go uphill. And the minus 4 should indicate to me that right about here at minus 4 is where the y-intercept should be. So if I graph, it should be a fairly steep graph, like this. Oh, by the way, I missed something on the last graph. Don't flip back, but I just want to point out here. I didn't label any points on this graph. You need to label some points on the graph. So what I really should have done is I should have labeled like 2 and 4. I should have labeled like -1 and 10. Does that make sense? So don't draw me a graph and not label points. You should label at least a couple so that I have some context as to where things are. Okay, so anyways, back to this one here. Does anybody know the method we use in our calculator to find where this does equal 6? Like where the output equals 6? Does anyone remember? That'll work. Second calculate. Now, value is very specifically for if you know the value of x. But we don't know the value of x. So we're going to do something called the intersect. But here's the problem with intersect. We actually aren't ready to intersect. Because to intersect, you need to have 2 lines. So you have to go back to your y equals screen, and you have to find 2x minus 4 as one of your equations. And the next equation is literally going to be 6. And if you go back and graph this, you should see now, here's your equation, and here's where like the line 6 shows up. And what we're going to be doing is we're going to be going backwards and trying to find which x value right here would give you a 6. Now that you have both equations in there, now we can intersect. So go like second calculate, intersect. The way your calculator functions here is it's going to ask you a question. It's going to ask you, where's your first curve? Curve because sometimes the equations we use actually will curve. These are straight lines. But so, are we on one of the 2 graphs that we need to have across? And I'd say yes. So I usually move like the side-to-side buttons, and I move the cursor in the rough vicinity of where they cross, like somewhere in that general area. Press side to side though. If you press up and down, watch what happens when I press the up button. The up button shifts me to a different graph entirely. So up and down toggles you between graphs. Since I only have 2 graphs, those are the only 2 choices. But theoretically, it's possible that you have 8 equations in there, and as you press up and down, it'll toggle you between your second equation and your first equation, and maybe even to your 6th and 7th and 8th of them. So I need to make sure that I'm on my first curve. Press enter. It should manually change me to the second curve automatically. Press enter. And then it asks for you to guess about where they cross. This isn't the end of the world, but do not assume that this is your answer. Your answer, by the way, was not 3.829, or whatever your calculator gave you. So you have to put the cursor relatively close to where they cross. The reason for this is that your graphs could cross in more than one spot. And your calculator is asking you to try to narrow down which one to go close to. And in doing so, pressing enter one more time says that x equals 5. So the way this would work then is that x equals 5, which, by the way, you guys could have just done algebra too, right?
Yeah, that's what I did.
2x minus 4 equals 6. Add 4 to both sides. 2x equals 10. Divide by 2. Divide by 2. You could have got x equals 5 that way too, by the way.
Can you do it that way?
So sometimes you can do it that way by hand, but the functions that we're going to learn about over the next 4 weeks, the polynomials, the exponentials, the logarithms, and the sinusoidals, doing it algebraically by hand that way isn't always possible. So you have to know how to use your calculator as well. If I could, let me do one last example, then we'll take a break. Can I skip down to the x-intercept one? It's okay with you guys? There's actually a function directly in your calculator that will help you find the x-intercept. Oh, by the way, we probably should have plotted that point. So there's a point over here at, what was it, 5 and 6? Plot that one. Where's the x-intercept? Right here. This is known as an x-intercept. It's where the graph crosses the axis that's going flat. The way we do this in your calculator is actually, there's a special function for it called a 0. So if you go second calculate the 0. Now this one actually operates a little differently than the intersect one does. It's going to ask you to narrow things down left and right. So the first thing you have to do is you have to make sure that you're on the right graph. See how currently I'm going side to side on the top graph here? So if you're on the wrong graph, press up and down to shift that. Okay. Then what you have to do is you have to get your cursor on the left-hand side of where it's going to cross. See how it's going to cross right about there? I'm currently on the right of that. So I need to keep shifting over until I get to about there will do. And I press enter. And what your calculator does is it puts a little arrow up top here, letting you know that it's now going to start searching for an intercept that way. But then you actually have to narrow it down the other way. So you have to go on the right-hand side of it and press enter. And that will also narrow it down. So what you've done is you've given it a search parameter so that it kind of has a rough idea of where to look. One more thing though, just like with the previous thing though, the answer is not 319 and 238 or whatever your calculator is. You actually have to put it relatively close to where the 0 is. The reason being is that maybe there's more than one intercept. So you got to put it close to the one we want it to be. And then just press enter. And it says that the x-intercept's at 2. So 2 and 0 is your intercept. So that rings some bells. Remember doing this? Cool. Okay, go take a 5-minute break. Then we'll do quadratics when you get back. So we're going to relearn all of grade 11 quadratics in the next half hour.
Oh, well, it's just review.
It is just review, so hopefully it's not something brand new. What we just covered then was essentially what you should have learned in Math 10C. Like I was chatting with Mr. Kwan, this is what he's doing with his kids right now. Yeah, hopefully you remember doing this before. Last year, regardless of whether you were in a -1 or a -2 class, you should have talked for a while about something called quadratics. And quadratics are another type of function, only rather than being in a straight line, they have like a curvy shape to them. And there's actually a name to the curvy shape. It's called a parabola. That's the official name. So, parabola. Parabolic. So, the main thing about a parabola is that it has what's called a degree of 2. Degree basically refers to the largest exponent out there. Do you see how this guy right here has an exponent to the power of 2? That's why it's a degree of 2. If I give you the equation y equals 3x plus 7, this x is to the power of 1, so that's why it's only to the power, yeah, that's why it's linear. We're eventually going to talk about things that have like 4x to the 5 plus 7x to the 2 plus 2x. So, by the way, I scattered a few worksheets around the classroom here. If you happen to have a duotang, can you throw that in the duotang you own? If you guys want to even just look at the sheet that I passed out here, basically it's just a list of all sorts of polynomial functions where the largest exponent could be like, say, a 3, a 4, a 5. That's my first job. The first type of function I have to teach you is we have to extend beyond linear and quadratics and go to things that are up to, I think you're expected to know how to get to the power of 5 or 6. So that being said, it's actually not that bad once I give you some basic rules to work with. So let's just do some more examples with parabolas then, with quadratics. So here's something to a graph. X squared minus 6x plus 5. So let's try graphing it. So go to your graphing calculator, get rid of everything else, and type in x to the power of 2 minus 6x plus 5. And I'm thinking go with like a zoom 6 just to make sure it's something like this. So if you can't get that graph on a nice like minus 10 to plus 10, plus 10. Yeah, hopefully it looks something like this. Well, I gotta be honest, neither am I. Like, this is my expectation. If you can draw that, I'm cool with it. Anyone not able to get that sort of picture of a graph here? Okay, here's my expectation then. And I even wrote this on that one worksheet there. When you draw the graph, you need to sketch a graph about as rough as you can, that's fine. You need to tell me the parameters from like 10 to 10, however that happens to look. And you have to label any key points. This graph, I would consider to have 4 key points. Anyone want to take a guess as to what one of the 4 key points would be? The y-intercept. That's a great one, yeah. So we'll start with that. The y-intercept would be 5, and I know that a couple of ways. One reason is it's the last number, 5. Another reason is I could go second calculate the value when x is 0, and it will show up as 5. So I would expect that on a graph you would label, and even though mine is nowhere near 5, by the way, I don't care. If you label this as 0 and 5, I'm cool with that. Okay? Yeah, put that into a table. Anyone know what another one of the key points would be? And there's 2 of them, by the way. There's 2 x-intercepts. So what we'd have to do here is go second calculate 0. And then we have to isolate them one at a time. So I'm going to slide this thing on both sides, one above, one below, and put it roughly in that vicinity. Sorry, I'm a little ahead of you. Hopefully you can get it to 1 and 0. Let me know if you can. So, second calculate the 0. Now, the 0, the x-intercept should go there. So I'm going to need to put it just slightly on that side. Slightly on that side. See how that arrow kind of narrows down the range? It's about there.
Okay.
Does that make sense?
Do you get 1 and
Anybody get the other x-intercept
I
yet?
got
5?
Did you get 5? Yes. I got 5. You got 5?
Awesome. There is another way, by the way, to find x-intercepts. You could go second table, and you could look for where it equals 0. And you see right here it equals 0 at 1 and 5. There's one big flaw to that, though. That would only work if the x-intercepts were whole numbers, like 1, 2, 3, 4, 5. What if the x-intercept was 9.3? You'd never see it that way. So I usually don't recommend going to the table for stuff like this. I recommend doing the 0 function. There is one more point I would expect on this graph, and it's called the minimum point. And on a quadratic, it's called a vertex. It's the very lowest point. And so to solve that, you go to minimum, because hopefully you'd agree that this point is the minimum lowest point you have, like a valley. And this one is another one of the left-right kind of things. So you have to put your cursor somewhere on the left-hand side and somewhere on the right-hand side of where your lowest point happens to be. It doesn't matter how far on either side, it's just you're narrowing down its search window. You do have to put the cursor relatively close and then complete your guess. So here's where your calculator might do something a little different than mine. Mine says 3.07. Anybody else say something?
Mine's 2.9. Yeah, mine's
Okay, so 2.9 repeating. Yeah. Like at the end of the day, would everybody agree that the number that's really close to this x value is probably essentially 3? So your calculator goes through quite a lengthy, I think it even uses calculus to solve this problem. And depending on how good your calculator happens to be, and I don't even know the other parameters, but you basically just need to round this number here if it looks something dumb like 2.999. So this is at 3 and negative 4. That would be my expectation. This is the vertex, is what we call that. Vertex. So I would expect when you guys draw a graph, like I'm going to have you do in that journal, sketch me like it would look something like this. Little bar like this, negative 10 to 10, negative 10 to 10. It looks something like that, and you should have 1, 2, 3, 4 points labeled. And that's all I'd expect out of you. The question that went along with this one here was, where does it equal negative 3? And I do this to illustrate a couple of points here. If I were to take y equals negative 3 and throw that on there, how many times does it cross?
Twice.
This is why when you use quadratics, sometimes there's 2 answers. Remember our first unit? When you had to solve things? Sometimes you solve and there's 1 answer. Sometimes there's 2 answers. There is also the possibility that you try to type in where it goes as low as negative 5. Does this graph go as low as negative 5? It doesn't. And this explains why sometimes when you use the quadratic formula, there is no answer is the answer. Right? Not that we're incapable of solving it. It's physically impossible to solve. The graph does not go that low. Wait, why don't you guys try this last... Do I have another example in here? I do. Can you guys skip ahead to this last example? Why don't you guys try this one by yourselves? Try to sketch this graph for me. And label all the key points. I'm going to come back to domain and range in a bit here. But find me the intercepts, find me any maximums and minimums. Sketch this graph just like we did the last one. So skip ahead to that last example. And we'll talk domain and range in a second. I'll come back to all those slides I skipped later. So long as you label all those key points there, even if they're not in the exact right spots, I don't care. So long as they're labeled right, then I'm cool. So, like if you see that it it's supposed to be at -1 and it's not there, then as long as it's in the rough vicinity.
So it's like the domain and range like 10.
Well, can I get to that in a second? I want you guys to all have a chance to sketch it first, and then I'll talk domain and range. With sketching it?
I sketched it.
Okay. Well, let me do at least this here for you. So you're able to type in 2 bracket x plus 1 close bracket squared minus 1. And I'm thinking a nice 10 by 10 graph probably is good, right? So, I mean, if this were me sketching this, I think it would look something like that, roughly.
Yep.
So, how many key points should you find here? I would say probably 4. Some of them are really close together, but I think you have 2 x-intercepts because it looks like it crosses the x line twice. I think you have a different y-intercept as well, somewhere hidden in there. And then you also have a vertex. So you got to try to find all 4 of those. So give that a try, and if you don't know how, I'll come troubleshoot you. So let's try to do x-intercept first. That's where you do a 0. So the way 0 works is you get to put the cursor like 0 there, right about there, and see how that's going to narrow it down? The x-intercept is right around there. It's at -1.707. Make sense? So then what we would do for you is, I mean, my graph right here, it looks like I'm at -3. I would just say this is at -1.707 and 0. Does that make sense? Let's see if you can find the other one. 2, 0. And I'm going to find your cursor wherever it is. So I'm just going to press the... Okay, we're over here at -9, which is way over there. So we need to move this way to try to find the cursor. It's off your screen. So I'm going to put it there. Down there. See how it's got those little arrows there? I'm just going to find that 0 right there. I'm going to put the cursor right around where I think it is. I feel like it's that. Okay. Anybody else having issues trying to find one of these values? Sure.
Well, the second no.
So I think the y-intercept goes second. Calculate the value when x is 0 is one of the fastest ways to do that. That'll find your y-intercept. The other way is with a table, and then your y-intercept is when x is 0, y is 1. So I'll steal that one. I just found this. There's a point there at 0 and 1. Sure. Oh. So you're doing the 0 meter? Okay, so then the other intercept is going around there. So we're going to put the cursor below over there. Put the cursor above over here. So it kind of narrows down the search window. I'll re-go back up with the cursor roughly where I think it happens to be. And so this will obviously need to write on the 0.2928, I guess. So this one is at negative 0.2928. And then the vertex is the minimum. And it's at -1 and -1. Here on the board are the 4 points that hopefully you should be able to find. Let me know if you can't calculate the values that is up there, and I'll come help troubleshoot you guys with one-on-one help.
Yes, sir.
You need help, or you got them all? You got them all? You should hopefully have 4. You should have the first x-intercept at -1.7. Then there's the minimum value at -1, -1. Then there's another x-intercept at -0.2928. And there's a y-intercept at 0 and 1. If you're good with your calculator, I have good news for you. This unit is very rinse, lather, repeat. I'm going to show you a graph. I'm going to ask you to find x, y intercepts, maximums, minimums, right? And you're kind of doing the same process over and over again. Only we're going to learn different graph types. So, here, why don't I show you some of the ones we're going to learn about, just so you have a bit of a heads up as to what they're going to look like. And then I'll do the skipped slides and talk about domain and range. Tomorrow, when we talk more about polynomials, we might do something like this. X to the power of 5 minus 6x to the power of 4 plus 8x minus 19. And we'll see what that graph happens to look like. One of the problems, then, that we're going to come across here, that doesn't look like much, does it? So we often have to monkey with our window size to get a better looking graph. So I might need to make my window size go bigger in the y direction. So I might go as low as like -50 to +50. And then I might see that I get a graph that looks like that. Even then, you can kind of see that the graph, I'm kind of missing a bit of a chunk down here. So I might need to make my y minimums go even lower. So maybe my y minimum go as low as -100. It's going to have a lot of wavy curves to it, eh? Maybe you can talk about that. Anyways, that's one of the functions we're going to learn. Okay. Another function we're going to learn will look something like this. 3 times 2 to the power of x minus 8. And that graph will look something like this. Very, very flat, and then it'll whoosh, kind of take off. That's an exponential graph. The third type of graph we're going to learn about is a logarithmic graph, which maybe you've heard about in chemistry before. If you took chem with me, we use logs in chemistry. It might look like this. 8 log of x minus 6 plus 7. And that graph, this one's kind of weird. The graph just all of a sudden just kind of starts over here and kind of heads that way a little bit. The last kind of graph we're going to learn about involves sines and cosines. It would be like the sine of 10x. This particular graph looks kind of boring, actually. But if you change the window size so that your x and y values go a little bit further, you let it go like from -1,000 to 1,000 perhaps, then the graph actually looks like this. And it actually goes up and down like a heartbeat monitor, which is kind of cool. So anyways, we're going to talk about those graphs later. Let me do the slides I skipped, then we can go. Okay. So one of the things that I didn't talk about, actually before I do that, is domain and range. I should do that one right here. Sorry that I'm doing this out of order. I didn't pack up yet. We're not done. Okay. Domain is your x values. On this particular graph here, there is every possible x value is allowed. There's no restrictions. There's no reason why we can't use an x value. Let me just show you an example of one of the future graphs we're going to do, though, where certain x values are not allowed. When we eventually do logarithms, we do the logarithm of 10x, for example. Here's what that graph looks like. Is there an x value of 1? Yeah, I think so. If I go second calculate the value of 1, it exists.
But not negative 1.
But if I try negative 1, see how it says y equals blank? If you like my vending machine analogy, it would be like, can you plug in $1? Sure. Can you plug in $2? Sure. Can you plug in negative $1? It's not really valid in this sort of question. But on this quadratic one over here, can you plug in negative 1 over here? Sure. So if every single value is allowed, maybe you've heard this phrase, x is an element of the reals. You guys seen that before? Basically, it's a short notation that means that any number you want, you can use. There's no restrictions. So we would say that that is your domain. That's your domain. No, that's your domain, not range. However, is every possible y value able to be used in this graph? And I would say no. Negative 10, for example, that graph does not go as low as negative 10 in the y direction. What is the lowest number this graph gets to? Yeah. So since it gets as low as negative 1, we would phrase it like this. Y has to be greater than, possibly equal to, negative 1. And I did that wrong because that's not greater than, that's less than. Y would have to be greater than or equal to negative 1. And that's how we'd write its range. You guys ever done that before? Okay. Most of the graphs we do involve one of those two things being an element of the reals. But the more graphs we learn over the next couple of weeks, sometimes there's just certain numbers that are not valid. Often negative numbers don't work. Sometimes like the graph just all of a sudden starts at a certain point and can't get any higher. Let me just show you one more of those examples. I did this graph a while back. It was 3 times 2 to the power of x all minus 8. As we look at this graph here, I'm going to go back to a regular window size, by the way. The reason why it kind of took off there is because I was going to 1,000 there. This is a little better. Does the graph seem to go lower than this section right here? I'd say no. It actually kind of flattens off. And we'll talk about that when we get to it. But I would say the range to this graph is y has to be greater than, it actually is negative 8, by the way. It's actually where it's lowest it gets to. Okay, let me do the last slides here and then we can call it a day. So what did I skip? I skipped this one here. Okay, terminology. This is a good example of a graph where it has most of the points I want you to label. X-intercepts, those would be points you should label. Y-intercept you should label. And if it has a vertex, you should label those points. If you happen to label other points, that's cool. But those are the bare minimum, okay? This slide just talks about the tools you need to know how to use. Let me just recap what they're used for. What is value used for? To find a y value if you have an x value. If you have x, it finds y. That's what value does. What does 0 do? Intercepts. Yeah, x-intercepts. You just have to know how to use it. You have to go on both sides. Okay. Minimum finds the vertex if it's the low point. The maximum finds you a vertex, but if it happens to be the highest point. And then lastly, intersect. Intersect is used if you have a y value, it can find you x. If you know that this y value up here is 7, it could tell you that x, actually have to be 2 x's on that one. Those tools are critical going forward. So hopefully you have a bit of experience with them already. And this slide here just talks about solving quadratics. It is possible that they never have an x-intercept, by the way. It is possible they have 1 or maybe even 2 answers. So it is possible, by the way, to have a quadratic graph that has no x-intercepts. which just means that there is no solution. There is no answer is a valid answer. Okay, I think I covered it all. Any questions? Okay, we're going to try something new here. I'm giving you an assignment. I want you to try to sketch 3 graphs for tomorrow. Think you can handle that?
No way.
So you got 15 minutes left. You can go now if you want to, or you can do it later. In the Duotang, in that one page I gave you, there are so many different equations. My recommendation, though, pick something that's either linear or quadratic, and I just want you to sketch 3 of them in your book for me. Does that work? I don't care which 3. So you can do it now or do it for homework. Sound good? If you want to take off, you can take off. That's fine. Well, we'll make it part of our next journal set, right? So, I think I need to remind you of this, though, because not everybody's been doing a great job in their journals. Right? People have been kind of very forgetful, lazy, not on top of things. So, try 3. Okay. I'll stop the lesson. So, if you want to take off, sign the board. If you want to stick around, you can.